the disaster that changed the entire engineering world. Engineering surrounds us. It's so woven into our lives that we rarely notice it until it fails. We travel on bridges, board aircraft, trust machines, and rely on systems without hesitation. We assume that every calculation has been checked, every material tested, every possible danger considered. We assume that engineering understands everything. But sometimes, the most devastating lessons come not from triumph, but from failure. Failures don't merely damage machines. They shake confidence. They expose the hidden assumptions we carry. They force entire industries to rethink what they once believed was safe. And in the middle of the 20th century, one such failure did exactly that. Its consequences reverberate through every engineering school, every design bureau, and every safety standard used around the world today. In the early 1950s, the age of jet travel was born. The world watched in awe as a sleek new aircraft, the de Havilland Comet, took to the skies. It was the first commercial jet airliner, a symbol of progress, speed, and modern ambition. No longer would passengers crawl over oceans in slow propeller planes. The future had arrived, riding on wings of alloy and innovation. But beneath this gleaming promise lay an unseen danger. In April 1954, tragedy struck. A comet broke apart in mid-air over the Mediterranean Sea. All 21 people on board were lost. At first, investigators were baffled. There were no storm conditions, no signs of pilot error, no obvious external impact. Then, just months later, another comet suffered the same fate. The aircraft disintegrated during flight, high above the Earth's surface. And then again, a third time. 3 catastrophic failures. 3 moments of sudden, unexplained collapse. The world watched in disbelief. And engineers, for the first time, confronted a terrifying reality. Something fundamental in their assumptions had been wrong. What was the cause? The answer was hidden in plain sight. The comet's fuselage, the cylindrical body of the aircraft, expanded and contracted with every pressurization cycle. With each flight, as the cabin pressurized at high altitude and depressurized on landing, the metal flexed like a bending paperclip being folded back and forth. These tiny deformations are normal in pressurized aircraft, but over time, something insidious began to happen. Cracks, microscopic and undetectable with the inspection tools of the era, formed near the corners of the aircraft's square windows. These were areas of concentrated stress, where the forces of pressurization and structural load interacted in ways engineers had not fully anticipated. On paper, the structure was safe. In drawings and calculations, it met all the criteria. But in the real world, with real stress patterns and real metal behavior, danger was accumulating silently. This phenomenon is known as metal fatigue, the progressive weakening of a material due to repeated loading and unloading. Fatigue doesn't leave dramatic signs until it's too late. There's no sudden warning, no bright red signal. Instead, it creeps in slowly, invisibly, accumulating damage with each cycle of stress. By the time the cracks had grown large enough to cause a sudden fracture, the comet fuselage could no longer withstand the stresses of normal flight. The structure failed catastrophically. The aircraft did not simply lose a part, it came apart. In an instant. And the consequence was devastating. Lives were lost, families were shattered, and the aviation industry stood still in shock. The immediate response was intense investigation. Engineers and scientists pored over wreckage, metal fragments, and flight data. They asked every question. Had the maintenance crews missed something? Were the pilots at fault? Were the materials substandard? But the truth wasn't superficial. It was deep. The failure was not a human mistake. It was a design oversight. It was a gap in understanding the very nature of materials under repeated stress. It was an assumption that because a part was strong enough to hold under one loading condition, it would be safe under thousands of cycles. That assumption was wrong. The findings from the Comet investigations revolutionized engineering. Fatigue, which had been a known concept in laboratory settings, became central to design philosophy. Engineers realized that to build safe structures, especially ones subjected to cyclic loads like aircraft, they had to understand not just static strength but dynamic behavior over time. They had to ask, what happens after thousands of flights, after tens of thousands, after years of continuous use? To answer that, engineers developed new tools, new theories, and new testing methods. Crack propagation theory emerged, allowing engineers to model how small flaws grow under repeated stress. Non-destructive testing techniques like ultrasonic inspection, radiography, and dye penetrant became standard ways to detect hidden flaws without damaging critical components. Design standards were rewritten to incorporate fatigue life calculations and damage tolerance criteria. Window shapes changed, rivet patterns were revised, and aircraft structures were redesigned to spread stress more evenly. Every aircraft flying today carries the influence of those lessons learned from the comet disasters. The windows you see on modern jets are rounded, not square, because corners concentrate stress. The materials used in aircraft are tested for millions of loading cycles before they ever leave the factory. And every new design is scrutinized with fatigue analysis tools that would have been unheard of just decades earlier. But the legacy of that disaster goes beyond aircraft. Metal fatigue is now central to bridges, turbines, pressure vessels, automotive components, and even biomedical implants. Anywhere materials are subjected to repeated stress, the lessons of the comet apply. The real lesson isn't just technical, it's philosophical. Engineering is not just about building what works today. It's about understanding what will keep working tomorrow. It's about humility, recognizing that our best assumptions may still be incomplete. It's about planning for the unknown and designing systems that tolerate imperfection. Failures like the comet disaster remind us that progress is not a straight line. Sometimes, progress is born from confronting the limits of what we thought we knew. Failures don't just destroy systems. They redefine standards. They shape disciplines. They teach lessons that success never could. And every time you walk onto an aircraft, drive over a long bridge, or step into a building with confidence, that confidence is built on generations of engineers who ask difficult questions. What if we're wrong? And how can we be safer? Understanding failure is just as important as designing for success. And that is why the comet disaster was not merely an accident. It was a turning point, a moment in history that changed the entire engineering world.